Okay, I think it's a good time for we to start today's webinar. So it's my great pleasure to introduce our speaker, Atif Ali Khan, who is currently a final year PhD student at the Building Service Engineering Department of the Hong Kong Polytechnic University. And his major research area is structure behaviors in fire environment. And he has previously been working as a professional fire engineer for 80 years, and also is a certified fire protection specialist from SFPE. And his PhD research focusing on the heat transfer analysis, structure fire, and CFD finite element analysis coupling, and also how the building collapse in fire. So it's my great pleasure to working with Atif as his co-supervisor. So in today's webinar, Atif will introduce a very brief history about how the fire modeling, how the fire models applied in structural engineer. So I'll turn my mic on to Atif.
And thanks for introduction, Dr. Huang. So I guess now everybody can hear me. So hello everyone, and thanks for joining this webinar. And I really want to thank the SFPE Hong Kong chapter for giving me this opportunity to talk. So I'm going to talk about how these fire models evolved within this during the course of time when the fire was occurring from long time in tall buildings and in small compartments. So as you can see in this picture, this is the picture which you're saying is the World Trade Center, where the fire was started by when the plane hit this building, and building was collapsed due to fire. So this kind of fire it was started by plane, but this fire occurs in many tall buildings we have witnessed, like Glasgow building in Iran, where these buildings were collapsed or failed due to fire. So how we are able to analyze this kind of structural failure now? So it's a very long journey where the structural engineers are able to analyze these kinds of buildings. So I want to give us some time and to appreciate the engineers and scientists who bring us here, and we are able to perform this kind of analysis. So let's dig and see where are we now and where we can be. So first, the fire was, if you go history of the humans, the paleontologist believes that it was the invention or controlling of fire when human learns how to control fire, and they were able to evolve as fast as that they control or other species, and they control over the planet. But the fire can be catastrophic as well if it's not controlled, and we have seen this one. That unfortunately human learns from tragedies, and especially if we talk about the engineers, they learn most from mistakes more than their success. And if you see these two pictures, they are representing two different times of fire, actually of the same city, when the London. This is the first picture is showing the fire which occurs in 1666, which is known as the Great Fire of London. During this fire started in a bakery, and it lasted for 4 days. And during this fire, almost 80% of London population was displaced. And but what it brings that the authorities and regulatory bodies come into action, and they try to enforce new standards and codes so that this tragedy never occurs. But if you go to 3 years back, the London bursts again, where the Grenfell Tower occurs, and in this fire, almost 80 people died. So what happened here? If you see the very interesting fact here, a fire which occurred like 350 years ago, where almost all city burned, but reportedly only 3 to 4 people died. But after 3.5 centuries later, in a relatively very small fire, 80 people died. What went wrong? So the main issue is here that the changes in the modern construction methods. We are changing our methods. We are making our building energy efficient. We are putting different products. We are making buildings very tall and different kind of sustainable materials, which are not actually sometimes not tested for how they respond to different fire behaviors. And we are not study. Of course, we are able in structural engineering, we are able to do that. This structure can survive to earthquakes. But in fire case, we are not there yet, and we have to work harder to go there. So you can see this fire, which is, I was talking about the grain fall. So fire was moving and reached to the top floor where we take the fire off. And this is the fire which occurred in WTC, which were 3 towers were collapsed due to fire. Of course, in first and two, tower 1 and 2, it was a plane which hit the target and the building was collapsed. But the tower 7, which was collapsed due to the debris of tower 1 and 2. But basically all 3 towers collapsed due to fire only. And this is another building which a fire occurred in Tehran, in Tehran 3 years ago. Also fire started in a shop, or a garment shop, where it occurred, and within 3.5 hours, this building was completely collapsed. So fire is causing failures of buildings. So what structural engineers do when they have to analyze a building and when they are designing the structure? They use different kind of loads to evaluate the structure. So that structure can resist to such kind of fires. Like, for example, they have to design a building so that it can resist to earthquakes. They will use seismic load. If they have to calculate how the building should react to the dead load and live load, so that your floor can sustain for such kind of load. Similarly, so that the buildings can react to the different kind of the thermal load. They will use temperature or heat fluxes as a thermal load, and they can do structure analysis, and they can find out how long this structure can resist to such kind of temperatures, and then they can perform the heat transfer analysis or structure analysis based on these thermal loads, which is applied based on this temperature achieved. So first, let's see how fire evolved within a compartment. Whenever fire started, the fire go through different stages. First is initiate, then fire starts growing and reach to the flashover. When everything, actually flashover is the condition when everything within the compartment starts burning. So when the flashover reach, and then its steady state temperature or fully developed fire reach there, and after that, when all components or fuel start decaying, and it go to the decay stage, or you can say cooling phase. So in terms of the fire protection engineer, growing stage is very important, because they have to design whether the fire alarm system will activate or not, whether sprinkler system should be activated within this period, and the most important, the people or occupants within the occupancies can leave the building. So you have to design the egress time. You have to calculate the egress time. So this is important for the fire protection engineer. But when we talk about the structural engineer, this growing stage is not very important. First, the temperature will not be very high here. And secondly, this is a very short period, like maybe like 2-3 minutes for a small compartment. So before it reaches the flashover, so maybe structural component like solid bodies will not be heat for that within this short period. So This is not very important for a structure engineer. They are mainly focused on the post-flashover fire situations or fully developed stage. So what is the basic physics to calculate this structural boundary so that structure engineer can use this thermal load? Actually, basically, we have to understand the three modes of heat transfer. One is let me revise the heat of these three modes of heat transfer is conduction, convection, and radiation. So conduction will occur within solid boundary. When you applied the temperature or thermal load to the solid surface or means structure boundary within the compartment, then these temperature will increase inside the solid through conduction. But what surface boundary we need only two modes of transfer. That is convection, which is basically because of the hot gases, which is started after when the fire started. These gases cover or structure boundary here, and this is so convection by gases and radiation from the flames or gases itself. So these two modes of heat transfer are important when you are calculating thermal load on the structure on the structure boundary. So total heat flux achieved at the surface is through convection, convective heat flux, and the radiative heat flux. For the convective heat flux, you have to calculate using simple Newton's law of cooling, and radiative heat flux can be calculated by Stephen Boltzmann's law. So one of the earliest work which is started by the end of 19th century or early 20th century, which is known as standard fires or standard time temperature curves. This is widely used in structural engineering. But what actually it is showing the ever increasing temperature until it reaches to the steady state. What happened is the testing agencies puts their structural components like beam and column, and they expose to the fire for a long period, and they provide these curves. So basically it is giving only increasing temperature. So they do not represent the real fire. Can you say that why I'm saying it doesn't represent real fire? Because there is no decay here. When I was showing you when I was showing there is a decay phase. So but these fires are not representing any decay stage. So basically it is not, but this is not the only case. Another case is not talking about the fuel load. Like where I'm sitting, the amount of fuel is different where you might be sitting, and the occupancy is different. What is the fuel load in office building is totally different. What is the fuel load in hospitals? So basically these curves cannot represent these kind of situations. So of course there is some limitation of these curves. And another important thing which will never change is the law of conservation. So when you have to evaluate the temperature and heat fluxes within boundary, you have to follow the law of energy conservation. For example, in a compartment when fire occurs, there is this controlled volume. So how much enthalpy is generated per unit time will be constant. So you have to follow these rules. So how much energy is coming in, how much energy is coming out from the control volume. For example, in this room, where how much enthalpy is added from the reactants, means the air which is coming inside the compartment, and how much energy or enthalpy is leaving out from the compartment. This is basically hot gases or the products of the combustion, and how much energy is generated here. That's Q. How much energy is generated from the combustion, and some of the heat will be lost to the structure boundaries, which is of course QW. So this is the law of conservation which will have to be followed or throughout the process. It will never change. So with this conservation, you can calculate the structure boundaries, heat losses, or their temperatures, and you can perform the structure analysis. So until we were using in these standard fires for a long time, then one of the revolutionary work has been performed by Professor Kawagoe in Japan in 1950s, or basically after World War II. There were many ruins of the World War II were available, so he did many testing there for decades. He was doing many tests, and he was able to understand that there's a relationship with the geometry of the compartment for the fire, and he produced this correlation where R equal to Ka under root H. So R is the burning rate. The burning rate is dependent on the area of the opening and the height of the opening. So he gives this connection, which was actually unique at the time. But unfortunately, this data and this work was still in Japanese for a long period until he met Professor Thomas in England. And then he started to develop this work in English and translated all of his work. And then it comes to the all over the world. And we were able to see that this is important correlation. So this is definitely indeed a revolutionary work at the time, which gives, especially in terms of the fire engineering for structural engineering. So that's why Philip Thomas and Kawagoe can be called the founding father of fire engineering in the structure. So, and if you see this R will always constant when you use for standard fire, but here you can see how much is changing. So let's give some time to understand this curve also, which is very important for even now. So this x-axis is showing the inverse opening factor, means this A under root H is in denominator. So here opening size is decreasing. So means your ventilation size is decreasing in this direction. So that's why this area, this region of this, we call as regime 1, is ventilation controlled. It means the ventilation is small here, and so limited air is present at here. But in this area, we call fuel controlled region, because ventilation is opening size is quite big here. So your fuel will keep burning until your fuel is present. Until fuel completely burned up, finished, the fire will stay. So there was no deficiency of air for a combustion. But in this case, when you are going to ventilation control fire, so fire will stay until you have air or sufficient air is present in this. So maybe fuel is present, but there is no enough air. So that's why it is called ventilation controlled fire scenarios. So this is which is introduced by Kawagoe. Once somebody asked Kawagoe what is his ambition actually, so he replied that he wants to abolish the structure testing. But of course, we are not reached there so far, especially, but we know the limitation of this testing, which you clearly understood by this. So in 1970s, after Kawagoe works, some of the important works has been done in Sweden in 1970s by Magnusson and Andersson. In Sweden, they did some study in Lund University. So they talk about that the correlation which is presented by Kawagoe or standard curve, they're mainly talking about the flaming phase. They have no representation of the cooling phase. So they said that the work what Kawagoe did and other, they suggested that this means the decay rate by 10 degrees Celsius per minute. And if you go to SFPE handbook also, they are suggesting like 7 degrees Celsius per minute. So this is all the prescribed value. There's no relationship with any physics or anything. So they're just the value they are suggesting from the empirically, they find different testings. So what they did, they tried to include this cooling phase temperature in the curve. So how did they provide? They follow the energy conservation equation and which equation which I showed you earlier. They try to solve it each term individually. So when they were solving, they first calculate where the neutral plane in the opening, so that they can calculate how much gas is leaving and how much air is coming in. So this neutral plane where the pressure is 0. So, and they calculate it using the simple Bernoulli equations. And using this, they were able to produce some factor from different experiments and they modify the correlation, which was I present earlier. They provide this factor and they were able to introduce new equations for the burning rate for all phases, a cooling phase as well as heating phase. And then the whole equation, to solve this one, they solve numerically using Rankata method. and calculate the structural temperature. So this was also one of very important work for a structural engineer. So whoever doing for structural engineering, I would suggest go through their work also. So using this Magnusson and Thielenderson work, it was extended by Patterson. He produced many curves for different fire loads. For different fire loads means like for office area, for hospitals, for different areas. So he produced these curves and for different materials as well, like for concrete, for steel, and he was able to produce many curves. And he provided the equivalent factor like the same curve, but if you have to use for steel, you can use one particular factor also. Some of these parametric curves can be found in Eurocode as well, Eurocode 1. So, but one thing is that these curves, because based on the experiment or numerical study, so they are limited to that particular size of the curve testing. So they are limited to 500 meters square. So more than this one, these curves are not valid also. So this is also limitation. And also they are providing, these curves are valid when the fire is fully developed. So means whole room or compartment have a single uniform temperature for the structure analysis. We will go through that, what's wrong with that. So one of the important work which I want to talk about, which is in 1980s, it was done by Margaret Law. She was the engineer. She was engineer in Arrow. So in 1980s, she extended the work of the Kawagoe and Thomas curve and explained more explicitly what is actually happening there. So she suggested that why there is a dip here. She said that in the field controlled fire, though burning rate increase, but because of bigger opening, the heat losses are higher. It means a lot of heat is lost because of the big opening. So there's a dip in temperature in field control region. And ventilation, as soon as your ventilation size is decreasing, your opening is decreasing, so your heat release rate is decreasing as well. So that's why there is a dip in temperature in ventilation control as well. So that's this curve is depart from some value, which is, she suggests around 5, or this size was around 12. So around 12, after that temperature will go down. So after reaching some maximum value. And she suggests, she also added in her correlation fuel load. So previously it was not added, and she added. So you can draw these curves for different fuel load. This was, that's why I say this is also one of the important study and needs discussion. So in the late 70s also, when the computer technologies were increasing and our computational hardware and software capability was increasing, and also we were trying to understand different kind of fire processes. We are trying to understand the dynamics embedded within for a compartment. So during that period, some zone model or field models or computer models were suggested at the time. So the most of the simplest one are zone models. They are, during these last 5 decades, almost hundreds of zone models has been suggested. They are very simple. So what actually zone model does, they divide the compartment in different zones. You can say hot upper zone, where this is the accumulation of smokes due to fire, and cold lower zone. So this, by solving the conservation of energy and mass and species, they were able to calculate the temperatures in both zones, as well as the layer height, so that they know how the height is decreasing. So, but they're computationally, they're providing very good results, reasonable results, but still there is a trade-off with accuracy, mainly because they are not solving the conservation of momentum. If they are not using momentum, so your velocity are not explicitly representing the reality. So that's also a issue with the zone models. So also in 1990s, what happened? One of the important work has been done in Japan by Ahasimi, what this suggests, these the curves we are talking about there, as I said, is uniform, and sometimes fire is not completely reached to the flashover. Fire is burning locally, especially if you say, for example, car parking or storage area, where the area is quite big and the fire is burning in particular area locally here. So in this case, temperature would be here would be different than far from there. So to understand this kind of fire, they call this localized fire models or localized fires. Hasimi in Japan, he performed many experiments and he tried to give some two correlations for two different situations. One, when the fire is impinging the ceiling. In another situation, when fires does not impinge the ceiling. So in both situations, he suggested that how to calculate the temperature on the structural boundary. So based on the diameter of the fire, means how big your fire is. So basically, if your bigger fire means bigger temperatures you will achieve. So based and the height of the room and at radial distance, you can calculate the temperature. So these are also one of the revolutionary work in this field to understand the temperature for localized fire. So these localized fire models can be found also in Eurocode 1 in Annex C. So if you want to calculate temperature for a long, bigger zone where the fire is occurring in locally, you can use Hasimi's curve. So it also added 19th, so not quite old. So another important understanding how the fire behave in large compartment comes when the fire is burning locally and then fuel is burned out, then fuel move and the fire moves further. For example, at time A, fire is here, and after time B, fire means your fuel is burned out and fire move to further. And for another time C, when the fire burned out here and fire moves further. So it means the fire is moving over the floor plates. So because of this moving behavior, we call this kind of fire traveling fire. And for large and open areas, for example, the decent office areas which are very large, so this kind of fire behavior is quite observed. Actually, this fire was observed in WTC, Glasgow building, and other large areas fire. You can find this there. So again, as I said, the temperature will not be uniform. So the curves which we suggested by parametric curves by Margaret Law or Thomas cannot be applied here. Here temperature is burning locally, but what are the temperature far? And fire is moving here. So you have to take advantage of some models at how far temperature is moving. So none of the previous curve can be applied such kind of fire behavior, and which is basically the more realistic than others. So one of the earliest work to understand this traveling fire was been suggested by Clifton. So what he did for a large compartment, he divided in different fire cells. He called it fire cells. Each fire cells he give the fixed value like 50 meters squared. So he suggests that each fire cell at one moment can be in one condition, like whether it's flaming, when this is fire, which is in flaming phase, or fire is already burnt out and it's in the cooling state, and the fuel, which is the fire cell, which is nearby the fire where the fuel is in preheat state. So he calls it preheat fire cells, and the other, which are only accumulation of the smoke. So they call this the smoke logged fire cells. So what he suggests for the flaming phase region or fire cell, he can use the parametric curves. So he used parametric curves here. And the preheat region and other region, he suggested fixed temperature. Like for example, the smoke region, he gives the 400 degrees Celsius. So within the range of 400 to 800, he suggested to use that one. And this flaming phase will be moving with some constant speed, like 1 meter per second or half meter per second, which is based on some experiments. So he suggested some values so that you can use for different fire scenarios. So he suggested it. This was, of course, this is very crude and simple and actually not representing the reality also, because parametric curves is for ventilated controlled fire scenario. But when your area is quite large, you cannot use parametric curves also, because usually for large area, fire would be most probably fuel controlled. It cannot be ventilation controlled. So two important models I also want to discuss here, which is suggested in 2000. One is by Professor Rain from Imperial University. Another was from ETFM by Shudai and his team. So unlike Clifton, they divided the room into two regions based on thermal condition: far field and near field. The far field is the region where the fire is burning and impinging directly on the structure components. And far field, which are basically, as name suggests, far from the flaming region, where the flaming is not there, but mainly because of smoke is there. So, but what Rain suggests in his model, he suggests fixed temperature within the near field. He suggests like 800 to 1200 degrees Celsius. You can use fixed temperature here based on how much fuel load you have. So fixed temperature in near field. And for far field, he suggests use to Alpert's correlation. So where each radial distance you can calculate temperature. So this is also one of the very crude way to calculate temperatures. Another is suggested by, as I say, Shudai. What he said for the near field in ETFM, for near field, they suggested to use localized fire model of Hashimi, like I suggest in 90s, which is suggested. So he suggested that you can use Hashimi's model to calculate temperature near field. But on far field, he suggested to take the smoke temperature by using zone models. So there are many zone models are available, so you can use, and he used the FIRM model, but you can use any zone model to take the far field temperatures. So this is also, but one thing should be noted, these all traveling fire model at this moment are the research stage. So you cannot you cannot find in any code and standard because they're not mature enough, because not many validation study has been performed. So maybe in the future they will become more mature. So then they can be added some more models will come, then they will be added in some codes and standards. So at this moment we do not have. So as I said that we do not have any models to suggest these kinds. So this is a limitation of the idealized fire models. So then it comes to full use of the field models, the full use of the CFD, which actually started after the tragedy of World Trade Center, to analyze how the building collapsed. In the fire scenario, you have no models, so they started using CFD, and because of the computer technology, the increasing processing speed, CFD become a little easier what it was in 1980s. But still there is a complex nature of the fire. It's very complex to do CFD and transfer data for the heat transfer analysis or structure or any finite element model, because there's a difference, because of the difference between the spatial and temporal discretization of the fluid and solid models. Let me reiterate again. Like if you are using CFD model for the fluid domain, the change in temperature is much larger, means rate of change of temperature in fluid domain is much higher than the solid domains, because the gas phase temperature will be changing very fast, but in solid temperature will change much slower. So temporal discretization is different. And if talk about the spatial, when you are doing CFD analysis or heat transfer analysis, you are using grid sizes. The grid size in CFD will be much bigger than the grid size used in structure. So sometimes in the CFD, the grid size would be even bigger than the structure. So it's not easy, it's not very straightforward to transfer the data and exploit all data from the CFD and do the heat transfer or structure analysis. So, but many models has been suggested by some researchers, and we also at PolyU, we try to couple FDS. FDS is a CFD tool which is developed by NIST. Sorry, I didn't mention earlier. So this FDS to connect with the open source, another open source finite element model, which is OpenSeas, and we were able to couple all these models. And if anybody is interested to do structural analysis using CFD or even other models, you can download this free tool from this website. And when this presentation will be available on YouTube, I will put these links for the user if they are interested in this and they want to use this CFD analysis as analysis for a structure. So we named this OpenFire tool. So this is where we actually now to analyze the structure and to how the structure responds to the fire. But again, this is, and one thing also I want to mention here, whenever you are performing CFD, the user must be very careful when you are using different boundaries and explaining the physical model, because change in any condition would give you a drastic result, because CFD is quite sensitive to each parameter. So be careful when you're using CFD. So let me summarize what I discussed so far. The fire models, which is suggested in 1900s, are early, so were standard fires. But I show you, but they are only increasing temperature. They're not talking about the decay phase. So we needed some changes there. In 1950s, the revolutionary work of the Kabagois and Thomas, they were able to understand some physics behind the geometry of the compartment and the burning rate. And later in 70s, some of the work which is done by Magnusson and Thiel-Andersen, which is extended by Patterson. So we were able to get the parametric curves for different fuel loads, for different materials. And because of the increment of the computer technologies, computer processing powers, and new software and hardware changes, we were able to use computer model in late 70s. And since then, we have a lot of zone models are available, and some are open source as well. And to understand the fire for non-uniform region where the fire is occurring locally, in Japan, Hasemi produced some localized fire curves in 90s. And when we reached in 2000, we are able to understand another fire scenario for the large area, because in the modern construction, your room size are quite bigger. So we suggested traveling fire models there. But again, I'd say that these traveling fire models are not mature yet. We are still far from that. And at this moment, now to represent the real fire, either you have to do experiment or you have to do simulation. But you cannot do experiment if you don't want to burn. If you want to analyze that how the structure failed like WTC, you will not do the experiment for that. As even you do experiment for large building, 10 times you do experiment, result might not be the same because of the nature of fire. So CFD is come for the rescue, and you can do the CFD and you can connect it with any finite element tool. And PolyU, we developed also one tool this is an open source tool where you can do coupling of the CFD with the finite element tool, any finite element model. Actually, we are giving the open source, so we use OpenSys, and you can download this one if you want to do this analysis. And thank you very much for you. This is how I'm going to summarize. I already summarized all, and if you have any question, I'm still here. And even that, if you have after that, you can ask me on my email. Thank you very much.
Yes, thank you, Atif. So if any audience have questions, you can leave that in the chat room. So I can pass that to Atif. I think it's a really good review from early work, like empirical study, to the Kawagoi's more scientific-based study, then to the computational based simulation, and more recent coupling between CFD and the finite element. So I think this is really nice chart and a good review.
Thank you. Thank you.
Also moving from the compartment files, the traditional one, and the traveling file, which is more realistic nowadays when we have large open office floor. So
yes,
it's more
exactly.
Okay, any questions? If you want to say something, you can raise a hand or some type something in the chat room. So I think maybe I can ask one question.
Yeah, please.
I think the structure part, what's its most challenge part for the structure simulation? I mean, steel is something easy to simulate.
Yes.
What about like concrete or other more complicated things?
Yeah, you mean when we are performing structure analysis, yes?
Yes.
So actually, basically for me now, I'm basically doing the transfer of the data, but how I'm doing actually the CFD analysis, the most, what I mean, the complication which I get here, mainly this, as I said, the discretization means how much, because when I'm doing CFD analysis, I'm not even adding any structure components. You need not to add. So you just take the temperature for this, like for example, I'm using like adiabatic surface temperature. So we just take this temperature and do simple heat transfer analysis for using these models in OpenSea software. So, but yes, as you said, for steel, we can take only one temperature on the surface. But maybe if you have a concrete, so you might need to put more thermocouples inside.
Okay. Okay. What's the challenge part about the? I mean, do we have enough data for larger scale test, or what can we do as a community to improve the capability of the model?
Yeah, actually, as I said, for CFD, of course, you cannot do any means, but for this traveling file, like for the, as I was talking about the RAINS models or EATFM models, I think we have to do many tests, means for the large compartments, which actually are many researchers already doing recently in malware and some tests in Italy. Many tests are going on, so we need more tests so that we can say that these models can make some sense, but still because they have all limitations. So we need still, and for CFD, you cannot use for large structure because for computational time it's too high. And you have to decrease the mesh size if you want to make it reality. For example, most of the tests has done for wood crypts. And if you are using wood crypts for simulations, if you want to validate this data, so you have to make a grid size very small. So which increase your computational very time, like for doing one computational for normal, even your like 20 cores computers, it will take like months. And maybe after that, the results might not be realistic or will not represent completely as equal. So this is a quite challenging part to validate. Especially wood crypts is very, all wood crypts are less than 5 centimeter. So your grid should be smaller than 5 centimeter.
I understand that. I see many large scale traveling file tests, but I rarely see any test burn the building down. So actually, do we need something like that? Actually, the building collapse in the test.
I think, yeah, that's very interesting what you said. Yeah, it would be very, it would be nice to do if we can actually do reality. That then we can say that, okay, our analysis is showing the failure. Because at this moment, what we did for WTC or Plasco building and use some hypothetical values. We can play with the CFD and we reach to this temperature and make the collapse. But we didn't do any structure collapse for testing. Yeah, you are right. If we could do that one, that would be amazing. Yeah, I agree with you. But at this moment, I think no one did that, as you said.
Otherwise, you can only analyze the past accident, and there's very little data coming out from the.
Yeah.
You actually need to do tests to collect more data.
Yeah. Recently, I'm doing one this Plasco building, and we have no information, and we are doing CFD for that. So it's very crude to say that we do same for WTC. for WTC, we cannot say somebody will do in a different way and can do, but they can make the collapse.
Okay, I see, Georgine, you ask a question. Maybe you can speak out. I already make you co-host.
Hello, Atif. Can you hear me?
Yeah, I can hear you.
Thank you for sharing. It's a very good presentation. And one thing I want to discuss with you is about the CFD and FEM coupling.
Yeah.
Of course, I think if we make sure the fire size is same and the calculation result from CFD, it should be lower than the engineer fire model calculation result, right? If we use the same fire size.
Yeah, actually for this one, as I said, it's CFD is very sensitive to any parameter. So you have to be very careful when you're using CFD, what parameter you are using. So maybe what you are not representing the model very clearly. That's why your temperatures are different. And as I said, this engineering fire model is also have some limitation. Mm-hmm. So there's a difference in both ways. If you are using engineering fire models, maybe you are missing some assumptions. So maybe that's why they're giving lower temperature, maybe not pure energy conservation. As I said, that the parametric curves, which is suggested by Patterson, are also most of the tests are for the wood cribs. So maybe for different material, it might not be the same. But in CFD and CFD, you are putting these values, and CFD has also some layer limitations. So it is very difficult to say that the CFD is completely representing the real fires and engineering model are showing. So currently engineering models is good enough for do reasonable, or at least you can give the qualitative, qualitative analysis. For quantitative is a trade-off of accuracy between both of them. So you have to, most important is you have to understand what assumption in both models you are using.
Yes, if we use it in the design stage, and we want to find out the worst fire situation, fire scenario, then if for structure analysis, maybe we just need the highest fire temperature.
Yeah, usually they do as a safety factor. They consider high temperature and put some safety factor like 10%, 20%. This is what actually structure engineer does. That's why you can see the standard fires is still quite famous, because they just give the very maximum temperature. So you already include the safety factor there. But of course, that's not reality. But if you want to do the real things and you want to save money, you want to estimate the cost of the project, so you want to go to reality so that you can reduce the cost. Means if you are making your building 5 hours resistance, but then you have to put a lot of money, and you want to reduce it if you put the reality. So at this moment, all these curves for a designer, they go for the worst case scenario. But we are moving toward the performance-based design. We have to save money for a project. So that's why we have to go through and suggest this kind of different models.
Yeah, I see now. Thank you.
Good discussion. Yeah, I think it's already like 1 hour. Let's thank the speaker, Atif, again.
Okay, thank you for giving me this opportunity. Thank you, and thanks for joining. And again, you can go for this our YouTube channel, and I will put these important links which I discussed in this presentation.
We will also put the video onto our YouTube channel. So if you want to review it, you can check it later. Thank you.
Thank you.